this is, as you remember, a slide from our last week meeting when we were considering Posse Flow, a flow of a liquid which is viscous, incompressible, between two plates. The lower plate was fixed and the upper plate was moving with a constant velocity. And we considered that the flow is stationary. So that allows us to kill the time derivative of a velocity in the Navier-Stokes equation, which is this blue equation. And then we in a configuration where the velocity is along the y direction, is in the x direction, and it only depends on the y direction, which is the direction on the drawing vertical, but just in between the length in between plates, then this reduces to two different ordinary differential equations. One that the pressure is constant along across the interface of the channel, and the other is that the Laplacian of the velocity reduces to the simple second order differential equation. So the solutions are very trivial, and they have to satisfy the boundary condition, and that's what we finally get. And now that is the same kind of a procedure we shall apply to the situation where we have a flow of a liquid between two plates which are stationary. So both of those plates, upper and lower plate, are held constant. And if they are held constant, then the flow goes along the x-axis. And there is a simple-minded physical analysis, which I sketched at the end of our last week meeting, that because the boundary condition for a velocity, viscous fluid velocity field on a fixed boundary, that it has to vanish, that means that the velocity will be zero at the bottom and at the top of the channel. And therefore, when it flows, and the velocity field is surely a continuous function, then there must be a point in somewhere in between those two plates where the velocity achieve a maximum value. And by a symmetry arguments, if they are both stationary and there is no gravitational field or anything which will distinguish what is up and down, except of the fact that I have chosen to label this place in a proper way on my drawing, then this velocity field must be also completely symmetric. It cannot choose one of the boundaries in a specific way. Therefore, the flow, it must have a maximum in between the plates, and by a symmetry argument, this must be in the middle of the channel, in the middle of the height, and it has to be a continuous function, and it is on a physical ground obvious that it cannot have any inflection or singularity point in the middle of a channel. Therefore, it must be something like a parabola. And actually, if you, and I strongly advise you to do this, try to solve the same equation we discussed for a channel with a moving boundary, then you get the following solution for a velocity field, namely that it is proportional to the gradient of the pressure along the x-axis. There has to be a flow of the velocity, the pressure gradient along the length of the channel, because if there was no pressure difference, then there will be no flow. There will be no mechanism to provide the flow. In a previous problem, the mechanism for a flow was provided by the moving upper plane. And the rest is a simple parabola. So this is an exact solution of a Navier-Stokes equation for stationary incompressible fluid. That is the exact solution of a simplified, in that sense, Navier-Stokes equation. And it is a parabola as far as the y is concerned. So the mean velocity now is not a constant value, one half of the, but it is just the something which is proportional to the gradient of the pressure, and the little h is the height. Is a height or a thickness of the channel, and I can repeat the same calculation as we did last week, and then the xy component of a stress tensor becomes a proportional to this gradient of a pressure. So with this, I can finish the problem, and I will now go on and solve the more complicated problem, namely the Posse flow through a circular channel through a cylinder. And this is something which is one of the most fundamental laws of the hydraulics. And as you know, most of our mechanical devices nowadays are based on hydraulic things. I mean, if you are pressing the brake pedal in your car, in most of the cases, you are using a hydraulic device, namely you increase a flow of the liquid through the brake fluid through some channels. So this Posse flow through a circular cross-section channel is incredibly important. The other application of that particular problem is what happens with the blood in our blood arteries all over our body. And the result, what is the amount of fluid which can goes over the circular pipe when there is a pressure difference between the intake and outer part of the pipe is a fundamental ingredient of the many physiological analysis of in biology. So that is a relatively simple but extremely important example of the applications of the viscous fluid dynamics. And let's try to solve it. Again, we have a Navier-Stokes equations, this blue equation, which we have seen just a few minutes ago. And in our geometry now, I have now, as it is conventional in the analysis of the problems with the cylindrical symmetry, I call the axis of a cylinder and that is the direction in which the liquid flows as a z, and I shall use the cylindrical coordinates to analyze most of the problems. Therefore, I have the other variable which is of importance is the radial distance measured from the center, from the axis of a symmetry of that cylinder. And because this is a cylinder, then it is obviously that nothing depends on the angle. There is no reason why there should be any particular angular dependence of the liquid. The system has a full cylindrical symmetry. So therefore the analysis will use only those two variables, the z direction along the pipe and or a channel or whatever, and the radial from its center. and the radius of a cylinder will be denoted as a capital R. So we have what is left from the Navier-Stokes equation is the eta is viscosity, this triangle is a Laplacian, and I should should make a comment that this is a triangle. It's not the capital delta, because we shall use also capital delta in some further calculations, so you have to be careful a little bit. And this is what is left from the Navier-Stokes equation. So now let's look at this, how we can solve that equation. First of all, the pressure difference is only along the z-axis. Therefore, the pressure is, by a symmetry argument, is only the function of a z variable. And now let's look at the Laplacian of the velocity. Well, the velocity has only one component along the z-axis, and therefore the Laplacian is actually a second order derivative in the z direction only of the only component of a velocity which I denoted as a script v. And this is also an incompressible fluid, and that means that the divergence of a velocity field is equal to 0. But because the flow is only in this one direction and it has only one component, v, the component along the z-axis, therefore the condition that the divergence of the velocity is equal to 0 reduces to the derivative of velocity with respect to z, which is only 0, and which is 0, and therefore the Laplacian does not depend on the z. And if it does not depend on the z, we have a problem with that equation, because the left side of that equation does not depend on z, and the right seems to depend on z. So how we can reconcile this situation? We can only reconcile the situation by an obvious assumption or a conclusion that the derivative of a pressure along the z-axis must be constant. Because if this is a constant, then there is no contradiction between the fact that the Laplacian of the velocity component does not depend on z, because it is just a constant. So everything seems to be all right. And I have now to figure out what sensible value is that constant. And by a dimension analysis, this is the derivative of pressure with respect to z component. So by a dimension analysis, that must be in units of a pressure divided by the length. And then it is obvious, the only length which is in a problem is the length L of the tube or a pipe or a channel through which the liquid flows. And the only quantity which has a dimension of a pressure which physically can enter this problem is a ratio of a pressure between the end and the beginning of between the beginning and the end of the pipe. And that ratio, the difference I have denoted as a delta P, and you have to be, I mean, it's obvious that there are different characters, but that is a delta, capital delta, and that's a triangle. So our equation now is had to be conveniently written in the cylindrical coordinates. You remember that I had shown you 2 weeks ago, I believe, a table in which I have shown you how the Laplacian looks like in a different coordinate system. It is relatively simple. It's a sum of a second order derivative with respect to the x, y, and z components in the Cartesian coordinates, but it is slightly more complicated algebraic expression in the cylindrical or spherical coordinates. And in the cylindrical coordinates, if you can check your notes, you find out that the Laplacian of a quantity nu, velocity, is a second order differential operator in the r dimension, in the r coordinate, plus a term which depends on the angle, azimuthal angle, and the z axis. But by a symmetry argument in our problem, that term, which I denoted as a L, is equal to 0. So what is left from the Laplacian in our configuration is only that radial term, and therefore I am having the following equation to be solved. And that is ordinary second order equation, differential equation, and the solution, general solution of that equation is of that form. It has three terms. Of course, it has a constant b, and it has a term which is proportional to the r square, and also it has a term which is proportional to the log of radial distance. And the constants a and b had to be fixed from the boundary conditions, and the b will be fixed from the boundary conditions on the wall of the pipe. But this logarithmic term, and the coefficient in the front of this logarithmic term must be identically equal to 0, because the log of r will be singular in the middle of a pipe. And there is absolutely no physical sense of to have a velocity field which all over logarithmically diverges in the middle of a pipe, and that is again a symmetry argument. Therefore, this coefficient a is equal to 0. So that is our solution for velocity, and velocity has to be 0 at the boundary. So that is very easy to solve now. And the final solution for a velocity as a function of a radial distance in the pipe or tube is a difference of a pressure between the beginning and the end of the pipe divided by the length of the pipe. So that's the pressure gradient, and inversely proportional to the coefficient eta. And there is again a parabolic flow. And in some sense, this result could easily be obtained from our result we just discussed before we went into the pipe world, so to say. Namely, we had this channel, flat channel, and we have shown that the flow is parabolic. So if we will just now bend the walls of this rectangular, of this parallel plate the walls, and weld them to form the pipe, then nothing basically could have changed physically. The flow will be still a parabolic, but it had, instead of having a plane symmetry, it had gained the cylindrical symmetry. So it is obvious that what was the y-axis in the previous calculation will become now the radial axis coordinate, and the rest is just a result of this bending and welding the plates into forming a pipe. So that is the solution for the velocity field. And with this, I can calculate easily the amount of a liquid which flows through the pipe, a cross section of a pipe in a unit time. I denote it as a Q, and that is just the density of a fluid times the integral of a velocity over the cross section. And the result is, again, a gradient of a pressure, now divided by 8 pi, and times the r to the power 4th. And this is the Posse law. The fact that the amount of fluid, the throughput of the fluid through the pipe is proportional to the 4th power, or the radius of the pipe, and inversely proportional to the viscosity, is this fundamental law of the hydraulics, so to say. And because in most of the hydraulic applications, the fact that the real liquids are not so incompressible can easily be ignored, with except of a few phenomena with which you might be encountered occasionally in your house, in your home. Namely, when you hear the voice in the pipes. That is, of course, the result of the fact that the liquid, the water going through the pipes is not incompressible. And if there are rapid changes of a pipe is abruptly changed and it has a sharp edges, then the flow at the sharp changes of the shape of the pipe become very high, and the approximation that the liquid behaves as the assumption that we ignore compressibility of the liquid becomes invalid, and we have to include the acoustic effects of the flow, and occasionally the flow may become so fast that the liquid evaporates and a bubble forms, an air bubble, a vapor bubble forms in the rapidly moving liquid. And then, of course, those bubbles grow and shrink and break down, and we hear the noise, and this phenomenon is called decavitation. And the other example of the fact where the assumption that the flow of a liquid is it cannot be assumed to be incompressible is a boiling of the water, because the boiling of the water happens that the small droplets, small bubbles of the vapor are formed somewhere in the volume of a boiled water, and those bubbles grow, and this grow is cannot happen in incompressible liquid. Therefore, those bubbles are growing in the compressible liquid, and they cause the noise. So that is the noise which you hear when you boil the water in your electric or gas kettle or whatever. So that is the solution for the Poisse flow. And the last example of the application of the Navier flows, Navier equations, which I would like to analyze with you, is a flow around the sphere. We had spent considerable time discussing what is happening when a spherical object, as a ball, is moving through incompressible barotropic ideal fluids. You remember we discussed the associated mass and effective mass phenomena, and we concluded that by the analysis of that, you understand that there is something which is called D'Alembert paradox, and that there's something obviously missing in the analysis of a physical phenomenon, which is a motion of an object in a liquid. That this assumption about the ideality of the liquid is of a restricted value. And here we are looking at the situation, what happens when we have a viscous liquid and we have the same ball moving in the liquid of the viscous liquid. And that was analyzed in a greater detail by the great mathematician and physicist, British physicist George Stokes, who was living at the turn of the 19th and 20th century. And usually this subject is known under the name of a Stokes Law. And here you have a picture. Imagine you have a ball which is moving now through the viscous liquid. You remember this drawing. These are the streamlines along the sphere, and they are basically the same, far away from the ball as in the ideal liquid. But you remember that there is a dramatic difference in the boundary conditions. The boundary condition for an ideal liquid was I'm sorry. You remember that the boundary condition for ideal fluid was that the normal component of the velocity was equal to 0 on the surface on the rigid boundary. And for a viscous fluid, it's not only the normal component, but also all the tangential components of the velocity. The whole velocity field must be equal to 0, because the assumption of viscosity is that the liquid sticks to the wall, to this rigid wall. And I would like to make now a short comment that you might ask a valid question. Is this a generally accepted situation that in all cases, the velocity field vanishes on the surface of on the rigid surface in contact with the viscous fluid? And there is a generalized boundary condition which has been proposed by the hydrodynamicians, and it is that the velocity field not only vanishes, but also a linear combination of a velocity field and its derivative do vanish. And that is a very, very interesting problem. What actually are the boundary conditions for a viscous liquid on a rigid surface? And the answer is outside of the realm of the continuous media theory. And in order to solve that problem, we have to go all the way back to the beginning of our lectures when we were discussing the statistical mechanical foundations of the continuous media. And we had to solve the kinetic equations of a proper form to analyze what is happening in the vicinity of a rigid wall. And that requires a detailed analysis how the particles, a real physical particle, out of atoms or molecules out of which the liquid is made, how those particles collide with the rigid wall. And you can imagine that analysis of that sort is not particularly simple. And it leads occasionally to the fact that the boundary condition that the velocity field is equal to 0 have to be generalized. This is particularly true when the liquids are far from the simple models of viscous liquids we are discussing. For example, those boundary conditions have to be properly adjusted if the liquid is a liquid polymer. Polymers are the long chains of molecules bound together, which are flexible, and they have degrees of freedom that they can rotate and change their conformation. And therefore, obviously, when the liquid of those lengthy objects interacts with the wall, then the boundary conditions become fairly complicated. But we are talking about the simple liquids, so we have that situation, and it is of interest to focus attention what happens to the streamlines when they are very close to the sphere. And it doesn't require any mathematics to observe that if that was an ideal fluid, then the boundary condition was that the normal component of the velocity that is perpendicular to the ball in that on the equator of the ball on this drawing is equal to 0. But when the streamline is very, 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 very close to the wall, then the velocity field had to be equal to 0. So something must happen, very peculiar on that wall. And this drawing is incorrect. There is something happening on the surface. And in physics, nothing happens abruptly in, at least within the continuum description. And therefore, when we have a viscous fluid which flows next to the wall of that ball, there might be a small region next to the wall where something funny is happening with the velocity field, and we don't have a tool to describe that so well using only the Navier-Stokes equation. And that problem, what is happening with the viscous fluid very close to the rigid wall, was a fundamental problem in hydrodynamics until the beginning of the 20th century. And it was eventually solved by a German hydrodynamician and physicist Rudolf Prandtl, who had invented the idea of the boundary layer, that we had to analyze in a special way a certain layer of a liquid which is adjacent to the rigid surface. And that boundary layer has a thickness which depends on the viscosity of a liquid and the velocity with which flow goes. And it is crucial to understand really how such a common device as the airplane really works. For it is what is happening with the boundary layer and how it affects the flow of a liquid around the wing of the airplanes is extremely important in the analysis of why the planes can fly. But Stokes analyzed that equation by not actually making any assumption about the boundary layer, and the solution for that problem, analytic solution, exists. And I was hesitating until this morning whether I should devote part of our lectures to analyze this solution, and I still have not made up my mind. And perhaps because the original solutions, I mean, usually given in the textbooks, are pretty complicated analytically, and but there are ways of solving that problem by using intuition and again symmetry arguments. And in case I make up my mind until tomorrow maybe on tomorrow consultation, I sketch you this, detailed analytical derivation, but you should not take my word for that I will do it, because I'm still not that certain whether this is worthwhile in the short time we have for those lectures to go in that analysis, particularly because I can basically derive the final result using the same technique as we discussed, and this is this dimension analysis. And assume that the sphere moves through that liquid at not too high velocity. And sure enough, in physics, when you say not too high velocity, then you have to have a gauge. What means not too high velocity? So let's make a mental note that the assumption which we are now making had to be quantified in what follows, because we will make an assumption that the velocity is not too high, and we shall later on think for whether we can really quantify and give a precise meaning to that word, that the velocity of viscous liquid is not too high. Then obviously the resistance, the force which is acting on the moving body, the resistance force, must be proportional to the velocity. And the only problem is to which power of velocity it depends. So this resistance power is proportional to the velocity to some power, which I call C. And sure enough, the force must depend on how big is that sphere. And the size of a sphere is surely measured by its radius. So therefore, the force acting, this resistance force, must be proportional to the radius, and who knows to which power. So let's call that power B. And then, sure, it depends on the viscosity. And we already have seen that there are some results which depends on the inversely on the viscosity, like the throughput through the pipe in the Posse flow. It was inversely proportional to eta. So we have no idea basically what should be dependence on the eta. We might guess that it cannot be too high power of eta, but let's just make an assumption that it is proportional to the viscosity coefficient to a certain power A. And there will be a numerical coefficient, which, as we already discussed, we cannot guess from a dimension analysis. And the only way to get the value, exact value of that coefficient beta, is through that complicated analysis, solution of a differential equation. So that is our guess for the force. So we write it up there on top, and let's look at the dimensions. The force in the Stokes Law, let me use that word, Stokes Law, is dimensionally proportional to the mass of an object, to a length, and inversely proportional to the unit of time, because the force is of that unit. And that must be equal to the dimension of a viscosity to the power A, dimension of a radius to the power B, and dimension velocity to the power C. All right. And I recall, and let's recall, the dimension of the viscosity coefficient is a mass inversely proportional to the length and time. That is easily to guess this dimensionality of eta, remembering that the units of viscosity is a Poise, and the Poise is a Pascal times second. And a Pascal is the pressure unit, and the unit of pressure is a force over the area. So that is very easy to find out using a definition of a force to guess that this is a proper dimensionality of the coefficient eta, of the viscosity coefficient eta. So now let's first discuss. We are talking about this not too low velocity. And you might remember that it is usually assumed that the resistant force is linearly independent on the velocity. So let's put the coefficient C equal to E, the exponent C to E1, then the force will be proportional to the velocity. All right. And now we plug into this expression, what is the dimensionality of a radius? Its length. So this is L to the power B. And that is dimensionality of the viscosity. So when we put it there, that the exponent of the length and time and mass on both sides of the expression must be the same. Because the eta is proportional to the mass, and there is no mass in other terms in this expression, that means that the coefficient, that exponent A must be equal to 1. So if we set A equal to 1 and C equal to 1, then we have the expression that the force is proportional linearly to the viscosity coefficient and linearly proportional to velocity. And the rest is trivial. The B turns out to be also equal to 1. And therefore, the viscous force acting on a sphere moving in a liquid has a very simple form. It's linearly proportional to eta, it's linearly proportional to radius, and it's proportional to the velocity. The only thing which is missing is that coefficient beta. And the beauty of the differential equation is that we can solve that problem exactly, and the solution gives us this coefficient beta, and the beta turns out to be equal to 6 pi. Well, it's not that entirely impossible to guess also the coefficient beta from dimensional analysis, but that is a kind of a riding over the band of the. So I'm not going to present it today, but we have a. So we guess this result. We guess the Stokes law without solving differential equation. And this is again a very simple-minded application of the dimensionality analysis, which is of a incredibly, it's extremely useful procedure in many hydrodynamical problems. So what remains is to find out the answer to the question, what does it mean, low velocity? And that is shown on the following slide. We have a Navier-Stokes equation, all right? And let's look at the dimensionality of various terms in that equation. What sits on the left side is the acceleration. The velocity is length over time. So time derivative is the length over time squared. Let's look at this term. It also has a dimensionality of acceleration, but it is, if the typical velocity in the problem is v with subindex 0, then a typical value of this term in this convective derivative is a velocity square divided by the length. And let's now look at the right-hand side. On the right-hand side, in the Navier-Stokes equation for incompressible fluid, we have a term which is a viscosity divided by the density. That is conveniently, conventionally denoted as a kinematic viscosity nu, but let's keep it for a while like this. And this is the velocity, and the Laplacian is having a dimension 1 over length square. So this term has a dimension of a viscosity coefficient, eta L square, and sure enough, I miss the coefficient. I mean, in this term there is also rho, so we will introduce this law in a moment. So I have two terms containing velocity on both sides of that equation. If the flow is stationary, that derivative, that is 0. And when I ask the question, which of those two terms containing velocity is more important in the solution of that equation, then I have to compare a typical value of that term to this term. So this is proportion to the velocity square over length. This is proportion to the viscosity coefficient times velocity to the L square. So the ratio of those two terms written in the square brackets, and I have reinstated the coefficient rho because the rho is here and it's not on this side. The ratio is the kinematic viscosity, that is the viscosity coefficient divided by the density, divided by a typical length and a typical velocity. And this is the dimensionless number. It's a number. For each value of the parameters, it's just a number. It doesn't have any dimensionality. And that number is an inverse of a number which is called the Reynolds number in hydrodynamics. And hydrodynamics is full of those kind of numbers which tell us what term in the complicated hydrodynamic problems is of some importance with respect to the other. And if the Reynolds number is small, then its inverse is very large. And if the inverse is very large, that is when the Reynolds number is small, then that means that this term, viscous term, is larger than the nonlinear term in the Navier-Stokes equation. So for small Reynolds numbers, in the Navier-Stokes equation, we can drop the left-hand side and retain only the right-hand side. And that is only correct for the small Reynolds number. And therefore, instead of using this assumption that the velocity is small in analysis of a Stokes flow, and we should use the assumption that the Reynolds number for that flow is small. And that means that the ratio of a kinematic viscosity to the length time of velocity is a small number, is a large number, because the inverse. So that is what should replace this vague statement that the velocity is too small. This is a beauty of the dimensional analysis, Because when we are saying that the velocity is too small, then we had to say with respect to what? So when we are saying that some quantity, physical quantity, which has a dimension, is small with respect to something, we have to provide the numerical value for with respect to what this quantity of the same sense it is small. And if we have a flow of a viscous fluid around the sphere, then from where we can get this other velocity to say that the velocity of a sphere is smaller with respect to the velocity of what? We don't have another other velocity. But it turns out that the Reynolds number is a property of our system and does not require any dimensional quantity definition. It's just a number. So each flow of a viscous liquid can be characterized by the value of its Reynolds number. And for small Reynolds number, we can easily restrict ourselves to the linear differential equation for velocity. But for a high Reynolds number, situation is very complicated. For a high viscous, for a very high Reynolds number, we cannot ignore the nonlinear term. And when you look up in your notes, you find out that I have shown you that in the Navier-Stokes equation for incompressible liquid, there is a general relation between a pressure term and the nonlinear term. Because when we apply the divergence to both sides of that equation, and when we apply the divergence, that means that we kill this term, we kill this term, and we get the relation between the nonlinear term in the velocity and the pressure. The rho is constant. And we can then, because of the divergence acting on the gradient gives us a Laplacian, we have this relation that the Laplacian of a pressure is given as a divergence of that nonlinear term, and we can solve that. And I had provided you with the solution for that equation, which relates the pressure to the quadratic form of the gradients of the velocity. And that relation between nonlinear terms and the velocity is valid for arbitrary Reynolds number. So for arbitrary Reynolds number, that means for large Reynolds number, we have to keep both sides of that equation, but the pressure term can be replaced by this complicated integral of a quadratic derivatives of the velocity. The region of a hydrodynamic phenomena where the high Reynolds numbers of a flow are of importance is what we will be discussing next week, and that will be called turbulence theory, and that is the one of the most beautiful and most complicated chapters in the whole theoretical physics, for we do not have really a correct mathematical description. We have various approximations, and we have lots of people, when we speak, working on understanding of what is a more general, as we understood now, property of the Navier-Stokes equation for incompressible fluid for high number Reynolds number, and except of approximate results and extremely beautiful and formulation of that problem, which which are given nowadays, we are still far, far from understanding, although we have a pretty good understanding of those turbulence phenomena, as we shall see, by phenomenological and dimensional arguments, and remarkably, that all great physicists have been trying to solve that problem, and they, in some sense, the best available analysis of that problem has been given by the congenial Russian mathematician Andrei Kolmogorov, a father of a contemporary probability theory. And I consider myself extremely privileged person, because as a young, very young man, I had a privilege to meet Kolmogorov and chat with him when he was visiting Warsaw, and that was a remarkable event in my life. So remember Reynolds number. The final chapter before the turbulence I would like to discuss is the linear wave problem in the hydrodynamics of non-ideal fluid, and that is how the sound is propagating in the barotropic flow. I will not be discussing any other sound propagation problems, only this, but the technique which we will use is something which is very similar to what is used in the other applications. These are the two general equations: Navier-Stokes equation for compressible fluid and the continuity equation. There are four of those equations, and we have four unknown variables: a density and three components of the velocity vector. So when we know what is the pressure, and as you remember, the relation for barotropic fluid is between a pressure and a density, and that is called the equation of state. And that is an example of what we discussed at the beginning of our lectures under the name of a constitutive laws in a kinetic theory. Then when we have it, then we can solve these four equations. We have a four complicated nonlinear partial differential equation, but if nothing works, we can put them on a computer and solve them numerically. And that is what is done in most of the contemporary applications. This is a term with these two viscosities, and and as you might remember, this bulk viscosity coefficient is for most of the liquids relatively small, so that term is altogether the eta divided by 3. Okay, so let me try to analyze those equations. First of all, I will use a slightly different notation. Namely, I will introduce the kinematic viscosity, and I will call that coefficient, which is a sum of a bulk viscosity and shear viscosity, as mu. So instead of complicated bracket, I have just two coefficients. And I consider that my liquid has an average density rho sub 0, and it moves with the constant velocity v0. All right. And now let me slightly perturb that flow. I mean that I change the velocity by a little bit which I denoted as a delta V, a small delta V, and the density of the liquid changes from the average density by a little bit, which I denoted as a delta rho. Okay, so that is my assumption. And let me look again and recall basically what is this term of a gradient of a pressure. In thermodynamics, a pressure for a barotropic flow is related to the derivatives of a Helmholtz free energy per unit volume, which is a small f. And the relation, thermodynamical relation, is a rho times the derivative of a free energy with respect to the density minus free energy. So that allows me to write 1 over rho times the gradient of a pressure as a simple term, a gradient of a density times a second derivative of a free energy with respect to the p rho squared. And this is a density-dependent coefficient, which I denote for the sake of a simplicity as alpha of rho. So this term is alpha of rho times the gradient of rho. So with this notation, my equation can now be linearized around the velocity v0 and the density rho 0. That means I inject here v equal v0 plus delta v, and rho is equal to rho 0 times delta rho, and I drop the quadratic term. So each term, each times I encounter a quantity delta rho, which is in a higher power than 1, or delta v, which is in a higher power of delta rho, of v, than 1, or if there is a product of a delta rho times delta v, these terms are ignored. They are considered to be small. Now it is correct to do the assumption that the delta v is small because we have the velocity measure. The gauge for velocity is v0. We compare delta v to v0. And that is, therefore, I need not to use the Reynolds number of anything else, because although I am making a dimension variable small, I have introduced the gauges for those fields v and rho, and they are set up by these coefficients v0 and rho 0. So this is the linearized Navier-Stokes equation. And as you see, it is an equation which contains, which becomes very simple, is linear equation. And the only, this is a gradient of a fluctuation of rho. This is a Laplacian of a delta v. And this is a gradient of a divergence to delta v. And what is left from the continuity equation is an equation, linear equation for a delta rho, which relates the delta rho to delta v. So now I have these two linear equations, and I have considered the coefficient. There are three coefficients, alpha, nu, and mu. These were the viscosity coefficients divided by a density. And in those linear equations, I had to keep only those terms of the nu and mu and alpha, which depends on the average density. Because if I expand the alpha, which is a function of a density, around the rho 0 plus delta rho, then the leading term is alpha of rho sub 0, and the next term will be proportional to the delta rho. So in that expression, it will be a nonlinear term. So I have to throw it away. So in all those equations, although I keep the same notation, the alpha, nu, and mu are a constant number. They are value of the coefficients alpha, nu, and mu at the average density rho sub 0, which I have shown here in this slightly invisible green letters. I apologize for using green colors. Apparently, they are not so well visible, those different colors than blue and red on the screen. All right. So these are my two equations. And how do I solve those equations? Well, because those equations are linear, then I can solve them by making the following assumption, that the changes of a density and velocity, those fluctuations, delta rho and delta v, are proportional to some coefficients, which are called delta with the bar and delta v, times a complex number, which is the x to the power I omega t minus I chi r. This is a general trick for solving the differential equation of that sort. And the only reason why I use the complex notation is that I am a little bit lazy, and instead of writing this fluctuation in terms of a trigonometric functions, I can handle equations in less space by using this complex notation. The x to the power I of something is a cosine plus e sine. So I'm looking for oscillations of those equations in that form. So if I inject this assumption into my equation, then the Navier-Stokes equation becomes an algebraic equation, and a strange term appears here. It's a consequence of the left-hand side of this equation. This is a frequency omega minus k times v0. The vector k is unknown, but it has its own name. It's called the wave vector. Similarly, as omega is called the frequency. And the unit of omega is 1 over time, and the unit of k is 1 over length. All right, so all of a sudden that denominator shows up, and this bracket shows up, and that bracket will play an important role in what we will see in a moment. And in addition, it will be hero of a short movie, which I would like to show you at the end of our lecture today. Hopefully it will work. And that is an equation for a density, and bingo, again, the same bracket shows up here. So now I have to solve those two equations, and that is a set of 4 linear equations for 4 variables: delta Vx, delta Vy, delta Vz, and the delta rho. And there are hundreds of ways of solving linear equations. But I will look at this, and I had rewritten those equations here. And now I first will look for waves which are transverse. What actually that means, transverse wave? If the wave propagates in a given direction, the transverse waves is that one in which the changes of a variable is perpendicular to the direction of a propagation of the wave. Because the propagation of a wave is set up by a vector k, then the easy way of looking up over transverse waves is to multiply the Navier-Stokes equation, to take a vector product of that equation with the vector wave vector k. So let's look what happens. If I take the vector product, then I have a vector product k delta v. And here I have a vector product of k times k. That's 0. Then I have the term, which is again the vector product of a k times delta v. And the last term is a vector product of k with k, so it's 0. So these two terms drop out in our, after we take the vector product. And we had a very simple expression, namely that omega minus kv0 is equal to the unit I times nu k squared. So let me put it back in our assumption that the time dependence of the solution is as a e to the power I omega t. If I put it there, then I get this term, and I have a term which is not oscillating. It's real term. And this is a term which, when time progresses, decay. So the transverse waves, the transverse solution for that equation are damped solution. If V0 is equal to 0, remember, V0 is the average velocity with the flow, which is constant. But if I have the liquid which moves with the constant velocity V and with the constant density rho 0, then I can do the Galilean transformation. I can move my Eulerian observator, because we are working in the Euler coordinates. Remember, we had a chapter on it. And if I change my Eulerian observer from a stationary frame of reference with respect to which the liquid moves with the velocity V0 to the frame of reference which moves with the velocity V0, then the liquid is not in motion anymore for this other observer. And in this other observer frame of reference, V0 will be 0. So that is the term which is related with the change of observer. And we have only a decaying solution. So the transverse waves in a liquid, viscous liquid, compressible liquid, are damped. And the damping coefficient is the kinematic viscosity nu. And that is a tremendously interesting result, for we see that the transverse waves propagates in the viscous liquids. They were not in the ideal liquid. And in addition, these viscous waves, the transverse waves, are damped. In the case we have time to discuss the elasticity theory, you will learn there that in the elastic medium, rigid medium, not in the liquid, there are also two kinds of waves, transverse and longitudinal waves. And both of them are propagating, are not damped. And therefore, there are transverse waves in the solid which propagates with the speed which is proportional to the quantity which is called the shear modulus. Here we have a damped wave, and the damping coefficient is the shear viscosity coefficient. It turns out that these quantities are related to each other. And there is another branch of continuous media physics, which is called Rheology, where this relation between the shear waves in solids and shear damp oscillations in the liquid, viscous liquids, are, so to say, combined to each other. And then the relation between the shear modulus in solid and shear viscosity coefficient in the liquids are discussed in some detail. So that's about the transverse waves. So that was easy. So now let's look up at the solution for the other waves in the problem. Namely, let's look for the longitudinal waves. And that we can analyze by taking with our Navier-Stokes equation the scalar product with the wave vector k. And for convenience in notation, I multiply it by rho zero. That's the equation will look slightly nicer. When I do it, then the equation becomes longer, but again, this bracket shows up. And now let's look. Here we have delta rho, and as in all the other terms, we have a scalar product of rho zero times k times delta v. And that is exactly what sits on the right-hand side of a continuity equation. Therefore, I can substitute in the Navier-Stokes equation everywhere, instead of this product of these three quantities, a left-hand side of the continuity equation. But that will generate a quadratic terms, a square of the bracket on the left-hand side. And that is the equation which I will finally obtain. Relation which we got for the transverse waves and this relation are called the dispersion relation. These are an algebraical expression relating a frequency of a fluctuation to its wave vector. For a transverse waves, that was a relation which gives us a damping. Here, a situation is more complicated because we have a quadratic equation for omega minus kv. That is not very complicated to solve that equation. And then you will see that the longitudinal waves are propagating and also damped. They will be damped by this coefficient nu plus mu. Okay, so let me look at this solution. I have reinstated here the value for the coefficient mu, and that is it. This is my equation, sure. And let's look at this for non-viscous fluid. If the viscosity coefficients are equal to 0, then our equation reduces to a very simple form. And that means that if I inject that, well, first of all, let's look at what is the rho zero times alpha. What is on the left-hand side is a 1 over time unit square. So the dimension on the right-hand side must be also 1 over time square. The unit of wave vector is 1 over length. So this, if we plug all the dimensionality, shows up that this coefficient rho 0 alpha, which is a derivative of a pressure with respect to rho at equilibrium, that is has a unit of a velocity square. And that quantity, rho 0 alpha, is conventionally denoted as a c square, and it is an adiabatic sound velocity. That is the velocity of a sound which propagates in viscous fluid. So the longitudinal wave solutions for the Navier-Stokes equation for compressible liquid is a sound wave, which in the non-viscous limit reduces to the normal sound wave, and for the viscous fluid is a sound wave which is damped. That is expression, dispersion relation in the non-viscous fluid. And in the viscous fluid, the relation is that, I mean, there's a still expression for non-viscous fluid, sorry. Then I can write it as the oscillation in time with the frequency omega, with the tilde, which depends on wave vector. And that depends on the wave vector is of this particular form. What is it, this relation? And this extremely simple looking relation for non-viscous liquid and its generalization for the liquid for a viscous case, which will have similar form, but omega tilde will also be a complex number. We will also contain a imaginary part which will lead to a damping. This is what explains a phenomenon which you have been encountered in everyday life, which is called the Doppler effect. You remember that when you are, this is always in the textbook for high school, that if you are standing on the platform on a railroad station, and there is a train which is approaching and departing, then the sound of a siren of the train changes when it is coming to you and moving from you, and they have this. This is a Doppler effect. The Doppler effect in hydrodynamics play an important role, and one of the tremendous progresses in the medicine is the use of the ultrasound, very high frequency sounds, to investigating properties of our body. And when you send the high frequency waves through our blood arteries, thick blood arteries in our legs and hands, in the particular arteries, then you can observe what is a Doppler effect, a change of the frequency of the propagating sound caused by the flow, by the rate of flow of the blood in the human veins. And that analysis allows us to find out whether there are any distortions of the flow of the blood in the arteries caused by the physiological changes. For example, by the sclerotic changes in it and so on. And you might have seen the advertising of the labs which do the ultrasonography, as it is being called in medicine, that they say that they can provide you with the Doppler measurement of the properties of arteries, and that all is related to this, what we just have solved. That equation is the basic equation for this tremendous achievement in contemporary medicine. And I found in the internet a film on a Doppler effect, which comes from one of American universities. And because the apparently new version of a keynote allows me to play movies in the presentation, so I have put that here, and we shall see in a moment where we can watch that film, and that film will be the end of our meeting today. All right.
Hi, it's Mr. Anderson, and this is AP Physics Essentials, video 108. It's on the Doppler effect. You've maybe heard of that before. It's why a siren, as it approaches you, you'll hear an increase in the pitch, and then it'll actually drop off. But it also could occur if you're moving, and we'll get into that in just a second. So let's say this point here is generating sound waves. They're moving away from that point, and so if you were to listen to them, those sound waves would be hitting you at the same rate, and so it would be a constant pitch. But watch what happens if we move that object from left to right. As it moves from left to right, you can see that the waves in front of it are bunching up. What would that sound like? An increase in pitch. And then behind it, they're actually spreading out. We'd hear a decrease in pitch. You could see the same thing in water waves. The swan, we know, is swimming from right to left. It's swimming to the left. How do we know that? Well, it's generating water waves, and the ones in front of it, you could see, are getting bunched up, and the ones behind it are actually spreading out. So that tells us it's moving to the left. It also has its beak pointed in that direction as well. Now, it's not only sound and water waves, but light is going to do the same thing. And one of the greatest discoveries ever was Edwin Hubble's discovery that wherever he looked out in space, all light seemed to be shifted to the red. We call that a red shift. What did that mean? All the light that he saw was moving away from us. And that indicated we were living in a universe that is constantly expanding. So Doppler effect has these amazing repercussions. And so waves and their observed frequency will change due to motion. And let's say we've got a source of those waves, and then we've got an observer. If the source of the waves is generating waves that move out, they'll be of uniform distribution unless it's moving. So as that source moves, as it approaches the observer, we're going to see an increase in the frequency of those waves. And then as it passes the observer, we'll see a decrease. But it's not only the movement of the source, it could also be the observer. As it approaches the source, it'll hear an increase as it goes towards it, and then there'll actually be a decrease as it moves away. And so let's give me a real example of that. Let's say you're standing there and a car is approaching you. The waves as they come towards you will bunch up. And then as it moves away, we're going to hear that kind of drop off. Why does that occur? As those waves come towards you, they're getting bunched together, and so the frequency is increasing, and that's due to the change in the velocity of that object. And so you'll hear increased frequency, and then it'll actually drop off as it passes you. Now we're going to experience the same thing, however, if we're moving, the observer's moving. So analogy works good for this. Let's say we're generating some waves on the left side, so the waves are moving from left to right. So if you're in a boat, you would feel those waves hitting you. But let's say now that you're moving, so the waves are being produced, but you're moving towards the waves. Since you're moving, you're going to hit them much more quickly. And so we're going to see an increase in the frequency of the waves. Let's say the opposite's occurring. Let's say you're moving with the waves. They're going to hit you at a slower rate. So you would experience a slower frequency, maybe a lower sound if we're talking about pitch. Also applies to light. So as the light is moving away from you, all of those wavelengths will actually be stretched out, and that creates light that's going to be simply moving towards the red. If it's approaching you, it'll actually be moving towards the blue. And so this is an example of that red shift that Hubble saw. Since everything was shifted towards the red, everything was moving away from us. And so did you learn to create a wavefront diagram to demonstrate why, as a source approaches you, the wave frequency increases, as it moves past you, it goes away, and also why movement of the observer can do the same thing? I hope so, and I hope that was helpful.
Let me show you the expression again. I hope you enjoy a little entertainment with the movie, but basically everything which was shown with those simple drawings and on the movie is contained into this expression, which we derive by linearizing a Navier-Stokes equation and then taking the limit of non-viscous fluid. All right, I believe that's enough for today. So let me now stop sharing, and I hope everything is fine, and we see each other tomorrow and next week on the lecture, and we will start talking about the turbulence. And as I said, I am still hesitating whether there is anything to be gained by going this complicated solutions of differential equations to get the Navier-Stokes, they get the Stokes flow derived, but maybe not. And that we shall see. And thanks for listening, and have a nice afternoon. Bye-bye.